evaluation of trajectory curvature using the natural method of the assigning of the motion of the material point is article number 8.3 of the book Mechanical Systems Calculations of the Marine Facilities. So let's consider the natural assigning of the motion of material point. So we have the trajectory of the point, we have the material point, and we assume for this definite one consideration that the starting point we indicate M. This is first position of the point after definite time. The point M moves to the point M1, and we have the natural coordinate system assigned with the point. So we have the tangential axis with the ort, the unit vector tau, and in the point M1 we have the another one location of the unit vector of the ort tau1. Let's move the point M1, the vector from the point M1, that ort vector tau1 to the point M. We will have the triangle MAB. And the A to B is the change of the ort, because the length of the ort no changes, but the direction changes, and we have the ort, what the difference of the orts when moving the point M by the way, by the trajectory for the increment of the arch, the small sized arch, like the increment equal to delta S. So when so let's consider the this is adjacency angle delta phi. Delta phi is adjacency angle, the same vector adjacency is here, yeah. And if we will tend the this increment, this very small size of the arch, to 0, that is point M1, we tend to the point M, which very small displacement of the point M. We will have the triangle MAB, and we can define the change of the vector of the ort of the natural coordinate system associated with the point M delta tau equal to just the angle, the adjacency angle incremental delta phi for the small motion of this point M along the way S here. So the increment model delta tau. So the increment one can find by angle the adjacency delta phi from the triangle IBM equal to tau product by delta phi equal to 1 multiplied delta phi. So that's just the delta phi because we have factor just equal to 1, the magnitude of the unit or tau. So we have this all to substitute into the equation for definite magnitude. What is the vector magnitude of the limiting magnitude of the increments of the change of the vector to the small way along the trajectory delta S arch, very small arch, and this we tend this arch size to 0. Then we have the this definite one magnitude. We say the vector of the curvature. We can define this as a derivative of the derivative by the variable reference the arch. The reference variable is a motion on the trajectory S. So on this derivative of the vector tau ort vector, the derivative of the vector by the variable, we have another vector. We say this vector is a curvature vector. This delta tau is increment difference of the vectors t1 minus t indicated here on the scheme figure H31A, and the vector of the curvature directed by the same as the vector of the increment of the ort, change of the ort delta tau, ort of the natural coordinate system moving together with the point M. So if we will consider this vector from the point M, I mean the vector of the change in the point M, this will be by this parallel direction as tau. So the definite vector of the curvature we defined by the derivative by the variable as a scalar variable, and tau is a vector, so the vector of the result of the differentiation, the vector direction coincides with the delta tau vector direction. Delta tau direction here indicated, but and yeah, and when we reduce to zero the increment of the arch of the motion of the point M along the trajectory, we reduce to the zero, we tend to zero. This vector of the curvature will gradually move to the main normal vector. I mean, the direction of the vector of the curvature coincides with the main normal vector, this vector of the curvature, to the center of the rotation if we reduce almost to zero the delta S increment of the arch. So this part of the arch, we can consider the segment of the circle. Segment of the circle, this is circle. So this is a curvature concept, and this is a circle of the curvature. So if we can consider a very small segment of the trajectory of the curvilinear motion of the point M from the point M0, assigned by the natural way of assigning this point. So for the very small, we can substitute by the segment of the circle, indicated here by the stroke line. But circle of the circle of the radius rho. What is the radius rho of the circle? We will consider a little bit about it. Radius of the circle. It's the arch length approaches to zero. So we consider the arch MM1 approaches to zero. Finding the limit, the radius of the curvature tends to the value at the point M. Rho 1 tends to the rho. What's the rho? Rho. The increment of the way of the motion along the arch of the trajectory of the motion trajectory point is related to radius and to increment d phi of direction rotation angle. So ds equal here was, if we consider the radius, this one radius, definite one radius, and so the delta s will be equal to the product of the radius by the angle d phi. Magnitude of the curvature of the motion trajectory of the point M when we substitute the denominator and the derivative by the definition of the increment of the reference variable S, the way of along the trajectory of the motion of material point by the segment of the circle rho d phi. So we will just reduce the common factor d phi in the numerator and the denominator. We will find that the magnitude of the curvature of the motion trajectory of the point M equal to 1 divided by rho. So the radius of the circle of the curvature, this is circle of the curvature with the radius rho, and the magnitude of this one vector, the vector of the curvature, is the derivative delta tau vector divided by delta s. Delta tau is a vector, so this is a vector value of the k, the curvature, but each direction is by the main normal to 0 point of the circle of the rotation. Circle of the segment, the point almost like moves in the rotation. If the point moving along the curvilinear trajectory of the radius a, rotation with radius a, r rho, with radius rho, and the curvature vector is equal to this curvature vector equal to 1 by the magnitude 1 divided by rho. Rho is scalar magnitude. So the magnitude of rho is equal to 1 magnitude of k of the curvature vector equal to 1 divided by rho. And the direction is n. This is main normal orth of the axis. So the direction of the curvature vector coincides with the direction of the main normal to the trajectory of the point, and the radius of the curvature of the curvilinear trajectory of the motion of the point M is the magnitude inverse to the curvature index. Curvature index K is the inverse magnitude to the radius of the curvature rho. The normal acceleration of the point depends on the radius of the curvature. So the rho we can find here, so we know that the normal acceleration equal to the velocity of the point v squared divided by rho. So the rho we can find as v squared, the velocity divided by the normal acceleration. Our questions and comments. The curvature vector of the point movement trajectory is the derivative of the unit vector of the tangent of the to the variable the moment along the arc trajectory in its natural way of being specified by the cardinal system associated with the moving point. Yeah, we found the curvature vector considering the change of the orths of the tangential axis of the natural coordinate system. As the orths of the constant magnitude equal to 1, orth is a unit vector. So then the change of the orth is the change of the direction of the orth. And finding the derivative of this orth as a vector magnitude to the increment of the of the motion of the point M, very small motion of the point M along the trajectory as the length of the arch along the trajectory of the motion point M tend to 0. Then we found that the vector of curvature by the magnitude equal, not by magnitude, but itself, the vector of the curvature equal to the derivative of the tangential axis of the associated with the moving point natural coordinate system. And the magnitude equal to 1 divided by radius of the curvature. Finding the vector of increment of orth of tangent to the trajectory of point motion by changing the direction of the trajectory. Yeah, by the increment of the angle of adjacency between the unit vector of the tangent of different places of the trajectory, the distance between which is equal to the increment of the point motion. We considered the triangle when we move the orth in the next point to the first point, original point of the motion of the point. The original location, we have two vectors, and these vectors, we have the adjacency angle between these angles. The adjacency angles tends to 0, while the motion of the trajectory is a smooth trajectory, while the way tends to 0. So the adjacency angle tends to 0, and the change of the vector depends on the adjacency angle and on the curvature of the trajectory characteristic. 833, the radius of curvature of the point motion trajectory is equal to the limit of the ratio of the tangent unit increment. Taking the model to the increment of the point motion tending to 0, yeah, the derivative of the angle of the adjacency between the unit vectors and of the tangents at different places on the trajectory, which with respect to motion of point on trajectory, which is a variable to which angle depends on the function. Next, we found the angle of the curvature of the trajectory, considering the dependence of the adjacency angle and the length of the way of the arch when the point moving the curvilinear trajectory. So finding that, we got that the change of the increment of the trajectory of the motion, the reference trajectory of the motion of the point along the trajectory, proportional to the radius and to the adjacency angle, the radius of the curvature and the adjacency angle of the trajectory. We got that. 834, the direction of the curvature vector of the point motion trajectory concerning the direction of the main normal to the trajectory in the natural way of specifying the point motion. As we introduce the curvature vector as the derivative of the orth of unit vector of the tangential natural coordinate system, then finding the direction Z, we find that the changes that the orth of the tangential coordinate system changes in the direction of the main normal, perpendicular to the the direction of the change of the orth due to the size of the orth magnitude remains the same, just equal to 1 unit, then the direction of the change of the orth is normal to this vector itself and directed to the center of the curvature of the trajectory. If we assume that the trajectory curvilinear in each small segment associated with the segment of the circle with different radius corresponding to the radius of the curvature of this trajectory. If we have the straight trajectory, the radius equal to infinity and the curvature equal to 0. H35, the curvature vector of the trajectory equals to division of unit vector of the main normal to the point trajectory by magnitude of the curvature radius. Infinite radius of curvature of a reaction trajectory, the radius of the circle, which is equal radius of curvature of trajectory moment along the circle. Yes, so the the definition of the magnitude of the curvature, we find this the derivative of the increment of the orth of the tangential orth of the moving natural coordinate system. So, and by the derivative by the reference variable is the size of the motion of the point along the trajectory, by definite small arch. We consider the arch of the motion by the curvilinear trajectory as the increment. So in numerator we have the change of the orth. In denominator we have the change of the location of the point on the curvilinear trajectory. So when we, instead of the location of the point on the trajectory, we substitute its redefinition by the radius of the curvature of this trajectory and the adjacency angle. On the other hand, the adjacency angle equal to the change of the orth, as the magnitude of the orth remains the same, equal to 1, and the change is only the inclining of the tangential orth to the previous direction of the orth. So we have instead of the numerator and the derivative, we can set the adjacency angle, and instead of the denominator, we can set the radius of the curvature multiplied by the adjacency angle. Exactly, I'm talking about the adjacency angle as about the increment of the angle. And after the mathematical transform, we find that this definition of the index of the curvature equal to by the magnitude y1 divided by radius of the curvature of the trajectory, as assuming this is a radius of the circle, if a very small segment of the trajectory, very small arch. The increment of the arch we assume as the segment of the circle. H36, the normal acceleration of point depending on the square of the point motion velocity along the trajectory and the radius of the curvature, inversely proportional when the point motion is naturally specified in the coordinate system associated with the point. Yes, a normal acceleration equal to the squared velocity divided by the radius of the curvature of the trajectory of the motion of the point. Therefore, accordingly, the radius of the curvature equal to squared velocity divided by the normal acceleration. Thank you.